Hi folks, this is the video tutorial for chapter 10 of my textbook. The title of the textbook is Composites Finite Element Essentials for 3D Experience, and the title of the chapter is Sandwich Plate with Foam Core and Carbon Epoxy Skins. So let me show you what the problem is. We have uh, a strip which is two carbon epoxy skins running along the length of the strip, and this is holding a foam core between them. Okay, the thickness of the skin is 0.05 inch, and the thickness of the core is 5 times that. So you might say, well, this is too thick. It may not qualify to do it with the way we are doing it, but it will give you good results. Okay. Now, uh, let me move on to the second problem, or at least the other slide. The loading on this structure is so that you're applying two moments at the two ends. Okay, and this structure is obviously made of, we're going to model it as 3 layers of composites, two carbon epoxy, and one foam. Uh, it is true that later I will be doing some chapters on modeling the core with solid elements, or what is called continuum elements in 3D experience. But in this chapter, we do all 3 layers with shell elements. Okay. The actually this geometry and the material is identical to that of chapter 2. Therefore, if you want to see what was done in chapter 2, either watch the video or go to the actual textbook of chapter 2. Now, I have also provided here the strength properties, but we are not going to be using these because these are used for failure purposes. I'm just trying to do analysis of uh, elastic behavior, which requires these properties. Okay. Now, it's coming from that reference, and the, when you look at the problem that we have at hand, we have two moments applied at the extreme boundaries, and this structure is under static equilibrium, but it's free to move as a rigid body. Therefore, I'm going to be using the so-called 1-2-3 rule, which was described in detail in the other chapters, so first chapters 2, 3, and we're going to be solving the problem. Okay, so let's go ahead and get down to business. I already have created a part here, and I call it video chapter 10, and we're going to make it now. So on a convenient plane, on that horizontal plane, I will sketch a rectangle that is 4 inch by 1 inch. Okay, let's dimension it. So this is going to be 4 inches. The width is going to be 1 inch. All right, and we exit. And fill it, F-I-L-L, surface, fill that boundary. So we have a surface now. Okay, save everything. Let me also create an access system which we will use as my rosette. Now remember, you don't have to create it here, because when you get down to the composite design workbench, if you don't have an access, it'll give you an opportunity to create it there. But I will do it while I'm here. So essentials, here's access system. It puts it at the global origin by default. Otherwise, you can move it if you wish, and it's allowing me the global coordinate system. Okay, good. The next thing we're going to do is to apply two materials, or create two materials. In all the problems that I've done so far, there was a single material. This is the first 9 chapters. Only a single composite material was present. Here, I'm going to need two materials. One of them is the actual composite carbon epoxy. The other one is going to be the foam, but the foam, although we're going to model it as a layer, we're going to be using isotropic properties for it. So let's go ahead and create first carbon epoxy. So you go to tools, create a material right there, create material. Let's give it a name, video chapter 10, carbon epoxy, carbon epoxy. Okay, and say okay. Uh, okay, so this is fine. I'm going to save this. I'm going to save my save my what I did, and now go to the browser, material browser, and you're going to see this appearing here. A video 10, video chapter 10, carbon epoxy. Okay, good. Now let me do another one. I can apply the materials right here, but not yet. So what I'm going to do is I'm going to say, okay, let's do another one. Another one. Create. This one is video chapter 10, foam. Okay. Say okay. Right here. Video chapter 10 foam, and the other one was video chapter 10 carbon epoxy. Okay, now we're going to start inputting our properties. So let's start with the carbon epoxy here. Right click, first the composite properties. This is unidirectional, and the thickness of that thing was let me see now, 0.05, I believe, 0.05 inch. Okay, so let's go ahead and do this. 0.05 is the cube thickness, and we say okay. And then we're going to input the simulation properties basically. So it's a structure, abacus multiphysics. We don't need a density. We're doing a static problem here. Elastic, and we're going to use lamina right here, and the properties that you had in the table. So this is going to be 20 e to the 6. This is going to be 1.2 e to the 6 psi. These are all psi. Poisson ratio for carbon epoxy was 0.25. This G12 was 800,000. 1, 2, 3, 4, 5. G13 also same thing. 8. 1, 2, 3, 4, 5. And for G23, I believe I used 40. Let me check this. Oh, these two are supposed to be for 400,000. Okay, sorry. So this one I'm going to make it a 4, and this one also 400,000. All right, and say okay. Now let's do and go and do the one for foam right there. So right click, composite. The thickness of that foam core is 0.25 inches. Okay, and the material properties, right click, simulation, again, structures, abacus multiphysics, mechanical, elasticity. This one is going to be isotropic, and the Young's modulus of it was 10,000 psi, and Poisson ratio was 0.45. I am sure that's what we had. Yeah, 0.45. Very good. And we say okay. Now, in the previous 9 chapters, what I did after I created these things, I had only one material, okay? I had only one material. And after I created my material, I then applied it. See that? Right click, apply to that part. Now here, you can do it. In fact, I did not even have to apply it there. Please go ahead and check it out. You see that I did not have to apply the composite the materials that are created to the part, everything would have gone through also, because these properties are going to be asked for when I do composite design. It's going to ask for material. It doesn't ask for the part. Okay. Now, here I can do it. I can apply one of these. I can't apply both of them. I can apply one of these, but I'm not going to do that to show you that actually you don't have to apply. Okay. So actually, I'm going to close this. But I created two materials. I want to have access to them. So the easiest way of doing this, as I mentioned in the book, you go there, you go to material definition, and it will give you the material properties for that are present in this session. So there's carbon epoxy present in this session, and there's a foam present in this session. And you can seamlessly go back and forth between the part and this information that you saw there. All right, let me just keep this thing handy. Let's save everything. All right, now we're going to go to the composite design workbench. And we're going to do a ply design because there's only 3 plies here. So ply design. And remember, you have to specify the composite parameters. You click on it, and the first thing that it's going to do is going to say, okay, what are the materials? So I'm going to say add a material from the library, and I select this tab that I created here, and I select carbon epoxy, and it's going to populate that table right there. And there is another one, of course. We have the foam, add a material, library, go to that tab and select the foam, and it's going to populate the table. Finally, the rosette, add a rosette. Remember, we created that rosette here from the tree or from the screen, right there. If it's too big, you don't like it, okay, change it here, maybe 0.5. This is cosmetic in nature, and there, okay. I don't need it. So okay, good. In fact, I'm going to hide that in a few minutes. Okay, I don't need that. Now save everything. We're going to create a plies group from that surface. Keep the draping direction up, that's fine. Plies group. Now plies is going to go into this group. This is the first ply, which is at the bottom of this plate. So for the contour, I select the sketch, either from here or from the tree. Notice it picks it. Under attribute, make sure it's carbon epoxy. All these orientations are 0. Okay, another one. Let's do this on that ply group. This is going to be foam, so same boundary though. We're going to change that to foam, and angle is 0. Now remember, this is isotropic, so it really doesn't matter, but we have to specify a direction, but we're going to make all of them 0. This is ply number 2. And the third one, in that group, same boundary, attribute, change this thing back to carbon epoxy, 0 degrees. Okay, and when in doubt whether you have done it right or not, you can go ahead and under review, look at apply exploder, and there we are, and apply. There we are. Now this is the one which shows that the solid right there. If I change that, it will actually do it as plates that you're used to. Okay, I don't need it. Everything was okay. The 3 of them were gray, which means they were 0 degrees. Save everything. Where is the save? Save. Okay, now we are done with the model, so we're going to go to structural model creation. Defaults, accept the defaults. Okay, notice that you have to create the element and properties yourself. So let's do the mesh first. So where is the mesh? Right here. There's the mesh, quad mesh on that surface, and the size of it is 0.125. So I want 8 this way and 20 16 that way. Okay, and nothing else. Quadratic. If you want, you can look at the mesh right there. There we are. Okay. Let's do the properties now. Now the properties, you have to go here. So you go to model under properties, and we want composite shell section. The support is that fill. Just gonna, yeah. And for the composite, we're gonna say select the plies. So it's asking for this basically. Oh, I could have picked it from here. I also picked it from the trees. The same thing. So that's fine. The other thing is that now let me repeat this. As soon as I say ply, it gave me this, but I didn't pay attention. I could have picked it from here. I went to the tree and did it. It worked. Now, as far as the advance, you're going to make sure that this has no offset. No offset simply means that the composite is half of it is above, half of it is below that reference plate. That's all. And this is it. All right. Now, there's one other thing I want to do here, and that is I want to apply the moment here to this edge and that edge. In order to do that, I'm going to create manual group. While I'm here, I might as well use that. Right, here's the group tab. So first of all, let me hide the surface. Right click, visualization. Let me hide the mesh. No, hide the model. Hide it. There we are. And say keep it there. And now we're going to do a manual group. So the first one is manual group number 1, and it's going to have all these 8, how many, 16, 17, 17 nodes here. Okay, so let's do that. So one, there are more efficient way of doing it. I didn't look into it. And remember, when you apply a load here, you have to take that 15-inch pound and divide it by 7 by uh, uh, 17. Okay, there's 17 nodes here. This is terrible. There is a more efficient way of doing it. Okay, and notice that 17 nodes have been taken, and say apply. Okay, good. And I do another one on this side. Notice that the group has been created here, right there. See that manual group 1 has been created. I do another one, and I'm sorry you have to go through this with me. Okay, so 17. I'm sure I could have made a box around that. There are different ways of making groups, and this is probably one of the worst ones for this particular problem. Okay, 17 selected. Notice that I have 2 groups here that I've created right there. All right, so let's save everything. We now go to scenario, structural scenario creation, structural, 2 red exclamation marks down here. So the first thing that we're going to go to setup, select the finite element model. That gets rid of the first red exclamation mark. You need a finite element model. And then we're going to go to procedure. We're going to do a static one, static step. The only thing that we have to do, it's a good idea to do it, is not to include geometric nonlinearities. So these are, You're assuming these are composites, things don't have large strains in it, displacement, so I uncheck this, uncheck nonlinear geometry. Okay, good. Now, we're going to apply our load. Okay, so let me right click here and get rid of the model. There we are. Okay, so first of all, the load. Now you go, look at this. We have forces, but in here you also have a torque, and moment is a torque. Okay, about the particular. Now it says, okay, what is the support of that torque? Well, all these nodes. So what I'm going to say is right-click groups. It tells you that you have two groups. Let's do this one first. Let's do the one in the front first. That's group one. So you select that. Okay. Now we got to be careful here because it is the torque about the y-axis. The y-axis is like this, okay? So it's this number, and it's 500 divided by 17, which I believe was 29 point some, 29.4, I think, 29.4. And wait a minute, now you look at this, if you look at the drawing, with respect to the axis that I have, this is a negative torque, okay, with negative moment with respect to the y-axis. So I put a negative sign here, and that's, oops, wrong place, right there, minus 29.4, okay, right there. See, this is how you apply the torque or the moment here. Let's do another one, again by group. It's the second one, okay, all right, but it is about the y-axis also. The only thing that is positive, y-axis goes like this, so it's going to be 29.4. That, right there. Now this makes sense. It's going to make bend like so. Save everything. Now this structure is free to move as a rigid body. Okay, therefore it's going to bomb out if I try to run it. I'm going to apply the 1, 2, 3 rule, and to do that, first of all, let me go ahead and hide these loads here. Let me hide the load. I guess you have to go and do it one by one. Hide and hide. Okay. So now we're going to go to restraints, fix displacement. Remember this point I decided to fix in all three directions. Oh, okay. So actually I have to hide the mesh, bring the model into the drawing, because I cannot apply, remember, you cannot apply nodes or forces and displacement to nodes. These are nodes, so that's no good. So I go there and say, bring me the model. Don't show me the mesh. I don't need the mesh. Now these things are bothering me. I'm going to hide them. I'm going to hide the axis. I'm going to hide, well, those planes are okay. They can stay there. All right, now we're going to say fixed displacement. This point, this corner point that I could not pick before, oh, not that. Zoom in. And part of the problem is that that sketch is blocking my view. So let me hide. Oh, yeah, this is one thing that I forgot to remind you, and I repeatedly said. Notice that I cannot pick that node because that sketch is blocking my view. So why don't you go ahead, don't forget to do these, go ahead and in the sketch, hide the sketch and hide the apply groups. I always hide the composite parameters too. I don't think you need it, but as a matter of fact, this time I'm not going to do it. Oh, okay, see, now I can select this corner point. Without hiding the sketch and the ply screw, you won't be able to take that. And all three of these are fixed. Let's do it on this side now. Another one, this point. This does not move in the direction Z, and it does not move in the direction X. Okay. And finally, this last one. Not the edge. I want this corner point right there. And does not move in direction Z. And we say OK. And we save everything. We're almost done. Now, we are ready to simulate, except that I want to look at my results ply by ply. So you have to ask for additional information. You go to simulate, see right here, it says output. To ask for additional output, you have to request it. So it's a stress component, and I want to request it by plies, by layers, which means by plies, and I want all three top, middle, and bottom section of the layers to be available. And this is a static problem, so field is going to do the job. We're good. Okay, if you want anything else, you have to ask it there. Now we are pretty much done. So let's go ahead and first of all make sure that there are no messages, error messages, warning messages. So start. Let me save it. It's always a good idea to save before you run. Because if something goes wrong and it crashes, at least you have the last save. So let's go ahead and do the model and scenario check status. This is okay. This one is for simulation check. Warning messages I can live with. Error messages, it's not going to run. Simple as that. This is not even running. This was simulation check. Even no warning messages here. Now we're going to run. This will bend down. As you will see. Okay, so it's a linear problem, therefore there is no iteration involved. It's gonna give you the answer pretty much in one step right away. And in future chapters, I will be modeling some of the cores. For example, a core with a continuum element. If it's too thick, you can use shell element. Okay. All right. So the first thing that's going to happen, the results are coming up. The first thing that's going to happen. Let me close this. Okay. First of all, don't panic, because notice that it shows you. Let me move these things out of your way. Because what happens is that this is a step frame 1, which is zero load. Here is frame 2. There we are. So this is the von Mises stress, but this is the overall top and the bottom. In other words, this is the von Mises stress on the top. You can turn it around and you can see the values in the bottom, okay? Because the top and the bottom may not be the same. For von Mises stress, it is the same, but when things are positive and negative and things like that, then of course it may be different. Now, let's look at the deflection. Okay, let me put this thing in isometric view. Where's the, right here, iso view. Okay, good. Now we can look at the displacement. There we are, about half a millimeter displacement in the middle. Now, if you want to see the stresses layer by layer, okay, this was von Mises stress, true, but it was overall. But if you, it doesn't tell you what layer by layer they are. So what you need to do is the following: you go to plots, okay. We are in plots already. You go to this contour plot. Okay, and then you're going to say, okay, I want stress component, not the overall, but for example, ply 1, which is the carbon epoxy, and I just want to look at the middle uh, surface of that ply. See, which ply, where, top, bottom, middle, and what is it that you want to look at? I want to look at, for example, the stress along the fiber direction, component 1, 1, and apply. There we are. You can see that. If you, for example, want to look at along 2 direction, apply, smaller. I also want to look at the same thing for ply 2. Now remember, for ply 1, I already did it here. You can see that. It was around 30,000 or something like that. Something along that line. Most of it is 30,000. Now, if you go to ply 2, if you go to ply 2 and look at the, for example, top section of ply 2, that's the foam, and sigma stress along the fiber direction and apply, look, it's almost nothing, 14 to 15 psi. So the core is doing its job. You put these things there, soft material there, which allows you to carry the load but develop very little stress in them. So that's pretty much it. Read the book for the, if you want, read the book please for the rest of the material, more detailed information. By the way, the results of this are matching the hand calculation through the ABD matrix from that reference that I showed you pretty closely. One last thing before I go, and that is you can also apply the, you can also plot the stacking configuration. You click on it and you select anywhere on that. This is gives you a stack. So this is carbon epoxy. Down here is carbon epoxy. This is the foam, 5 times the thickness of these two, and they all have orientation 0. And you can also get the ABD matrix. B is 0 because it's a symmetric ply configuration. But here's the matrix A and here's the matrix D. A is good for in-plane deformation and D is good for bending deformation. Good luck.